So let's get started with the second session. So it's my pleasure to introduce Lisa Bachmann, going to be talking about advancements in hydrogen combustion simulation using lookup tables. It's all yours.
Thank you. So welcome back from the break. I hope you all enjoyed another coffee. Just take a lot. The coffee is really good, I think. So for the past months, together with Avid and ISOF, wait, I need to close Grammarly here. Together with Avid and ISO, I've been working on advancements in the flame-generated manifold that Avid already talked a little bit about in his talk. For short, flame-generated manifold is going to be FGM. And the goal is to simulate laminar hydrogen combustion. No, I'm just going to do it like this. Oh, it's not working?
Can you try the clicker again?
Yes.
There you go.
Okay, perfect. So firstly, why do we want to simulate hydrogen in the first place? Bosch's goal is to redesign burners to make them suitable for large percentages of hydrogen. Why hydrogen? I think it's pretty obvious. In the hydrogen reaction equation, we don't have any carbon. And what do we need to redesign these burners? We need to make sure that we have low emissions of NOx. We need to make sure that we maintain the thermal efficiency. Of course, we need to make sure that the burner is still safe. And also to make it financially make sense, we have to ensure a great lifetime. So all in all, we can say that our goal is to be able to have an efficient simulation of hydrogen combustion. So when I went into this topic, I was like, why is it so difficult to simulate hydrogen in the first place? Because there's also already a different combustion simulation. The problem with hydrogen is that it has a very fast molecular diffusion. The molecular diffusion is much faster than the thermal diffusion. This means that locally we have concentration gradients. These concentration gradients then lead to an additional diffusion term. I will call this additional diffusion term the preferential diffusion in the next slides. At this part, it's important to mention that for turbulent combustion, this preferential diffusion would not be as important because the preferential diffusion would not be as important because the turbulent diffusion is much more important. But for the burner flames that we want to simulate here, they are laminar, so we really need this preferential diffusion. Because of the different concentrations in the domain, we also have a different issue. We need to introduce the mixed refraction as an additional independent variable. The mixed refraction here describes the fuel-to-air mass ratio, mass fraction ratio. And on top of that, hydrogen has a very high flame speed. So in general, we already have a high risk of flashback, which we, of course, need to prevent due to safety. So at the moment, we already have some possibilities to simulate hydrogen combustion. On the one hand, we have the possibility to do it with detailed chemistry. The problem with detailed chemistry simulations is that we have to solve many equations. So with a high computation cost, we're only able to simulate very small domains. In SU2, at the moment, we're already using a flamelet approach. Flamelet approach means that we're utilizing one-dimensional Cantera flamelets. We combine a lot of these one-dimensional flamelets into lookup tables, which we can then use for the simulation. However, these one-dimensional Cantera free flamelets have a big issue. The issue is that they do not assume any external heating or cooling. However, when we have the burner, we have external heating or cooling due to the walls of the burner. So this leads to an overprediction of the source terms. The source terms are the initial conditions for energy release to the surrounding. For short, that means that Cantera predicts more energy release than there is actually, which means that Cantera predicts the flashback much earlier than it actually happens. And because flashback is like safety relevant, that's not that good for us. To sum up, like the current state, we can say that the detailed chemistry results or the detailed chemistry simulations are really good for validation of simple use case. That's also what I'm going to use it for in this task. However, they're not really usable for like bigger simulations, of course. And our goal is to improve the flamelet approach to eliminate the overprediction of the source term. We are going to do this by, on the one hand, improving the lookup tables and improving the generation of the lookup tables, and by, on the other hand, improving the implementation in SU2. So how are we improving the generation of lookup table? On the right side here, I put you an image of a one-dimensional flamelet. You can see at the bottom here is the unburn, then here's the flame front, and then it just heats up over to the top. This progress of burning, you can also show over the progress variable. So you can see here on the x-axis is the progress variable, and on the y-axis is the temperature. So the progress variable just tells you how fast the combustion has already progressed. That's why it's called progress variable. On the bottom graph here, you can see the source of the progress variable. The source of the progress variable represents the initialization of the progress variable. In this graph, you can see it really well. So if you have the peak and the source of the progress variable, shortly after you have the temperature rises faster than it did before, which means that the combustion progresses faster. Normally, the flame can get described by the progress variable, which again indicates how fast the combustion progresses, and also by the enthalpy. Due to the preferential diffusion, we have this change in concentrations, so we need the mixture fraction as a third independent variable. So here on the top right, I put you one singular one-dimensional flamelet as a function of enthalpy, of progress variable, and of mixture fraction. What we are doing to generate the lookup tables is we combine a lot of these one-dimensional flamelets, which is represented in gray here. And from this data, we then generate a lookup table, which is three-dimensional with the different levels. You can see here in the red for different mixture fractions. So now what did we actually improve? For the lookup table, we had the problem that we already have this overprediction of source terms. Due to the Cantera flamelets not taking heating or cooling from external sources into account. On top of that, we had the issue that our domain for the singular flamelets was actually only this area in the middle. So we were cutting the singular flamelets too far. So on top of already having a too high source term, the source term at the edges was on top of that too high. So what we did was we widened the domain, and with that, in our simulations, we were actually able to achieve source terms of 0 at the inlet and at the outlet, which was not the case before. On top of that, we enhanced the mesh refinement. Lookup tables are very they need a lot of memory, so you really need to make sure that the lookup table in general does not get too big. However, we had the problem that we wanted to save so much memory that the lookup table was not refined enough, and in the areas with a lot of change, we just had a lot of error. So we were able to just enhance the refinement so that it is just big enough while being small enough to actually run with a decent amount of memory. In the SU2 code, formerly the preferential diffusion terms were just added in the whole domain. This led to stability issues, and now we only add the preferential diffusion once the combustion has already progressed. So in the unburned, we only add the regular diffusion terms, and then when the combustion has started, we add the preferential diffusion terms. On top of that, we had some issues with the CFL adaptation in combination with the spark initialization. If you do the spark initialization together with the CFL adaptation, by the time the spark actually is there, your CFL number is already so high that the flame either immediately flashbacks or blows off. So what we did is we implemented an additional parameter to the adaptation that basically just states when the adaptation is going to start. So for example, if you have your spark starting after 500 iterations, you can now say that you want your CFL adaptation to start after 1,000 iterations, which really makes the whole process of initialization of a new case much easier. So now let's go on to the validation. So here I have an isothermal case. You can see that it's isothermal because the burner, which is here, is at the constant temperature of 450 degrees. No, 450 Kelvin, sorry. On the left side, you can see the detailed chemistry results that we always use as validation. And on the right side, you can see our FGM simulations. You can see that in general, the agreement is pretty okay. However, the FGM flame length is consistently shorter over all the different inlet velocities. Why is that? That is because we still have an overprediction of the source terms. The source terms are still too high, which means that the heat release is too high, which means that the flame length is shorter. If you look at the actual source terms, you can also see this. So on the y-axis here, we have the source terms, and on the x-axis, we have the progress variable. In red, you can see the detailed chemistry results, so how it should actually look like. And in black, just above that, you can see our FGM results. So you can see that even though we did some improvement already, the source term is still consistently too high. What are we going to do about this? So the first idea or the first option was to only correct the progress variable at the low, correct the source term at the low progress variable. So at the very unburned side where you can also see the circle. This limits the burner heating, which already helped a lot with flashback, which actually allowed us to get converging solutions in the first place. Because before that, the burner was just heating up and heating up until we got to flashback. However, we still, as you saw here, we still have this lower flame height. So it is not in this correction. It is not really possible to generate to simulate the flashback at the correct position. So we also tried out another option. Vance and et al. In 2023 proposed a correction term that is looking like this. So the idea is that you multiplicate this correction term with the source term. So it is depending on the equivalence ratio, so on the mixture of the inlet and on the temperature. So for this case, or basically for all cases, you can see that for a temperature higher than 1000 Kelvin, it is not doing any correction at all because the correction term is at 1. The problem we have with that is that the border for 1000 Kelvin is in the very middle of the domain. So if we apply this correction, it would mean that all of this overprediction of the source term does not get corrected at all, which means that sadly, this correction is not applicable for our case. So the next step would be to actually develop our own correction. In our opinion, it should also not depend on the temperature, but rather on the enthalpy. And also it should include factors for inlet velocity and burner properties to make it as applicable for multiple cases as possible. However, we are still looking for that better correction. And at the moment, we're just using this correction at a low progress variable because it allows us to get stable solutions. And we just have to live with the fact that we're not able to simulate the flashback position correctly. So lastly, I also have some validation simulation case on the conjugate heat transfer. So here we actually don't have a constant burner temperature, but instead we let the fluid heat up the burner. And this basically just is another argument as to why it is important to have the right source term prediction, because you can see here that the source term is also overpredicted. And you can also see in these cases that the temperature in our simulation is just way higher than in the detailed chemistry simulation. So to sum up, we were able to improve the lookup table generation to limit the overprediction of the source terms. We also were able to improve the simulation stability, and we were able to achieve cases without flashback, which was an improvement. And we also implemented the Vance correction. However, we found out that the agreement with the detailed chemistry simulations is still not perfect. The Vance correction sadly is not applicable for this test case and probably also not for most other test cases. And we are still over predicting the source terms. So our next steps will be obviously to further improve the source term over prediction. We want to find an alternative to the Vance correction, and we also want to look if we can make any additional improvements to the SU2 code. If we are able to do this, the next step would be to validate the LME generation. So we already have a way of taking the data from the lookup table to the MLP. So we have a way to train it, which we just need to validate it again. And then, of course, the further step would be to also do this in 3-dimensional cases. So thanks a lot. And I'm really curious for your question.
Okay, questions? Boss.
Dass you remark that people use no networks to achieve that outside because that is what's involved. I also thought that even that total processes are much more readily very explicit in what they're doing than we talked about weeks. So it's something maybe want to try a bit more explicit method.
Okay.
So I think those like very and so having full change that.
Perfect. Yeah. Perfect. Thank you.
Other questions? And from the overall prediction of the sources, was this ratio purely the population or due to preparation distancing effects? Like how did the mixture work between the here?
So we are pretty sure that it is due to the preferential diffusion, because I also did simulations without preferential diffusion. And there the agreement between the detailed chemistry source terms and the FGM simulations was pretty good. So without preferential diffusion, all of these cases were perfectly fine, but that doesn't really help us if we want to simulate hydrogen.
Very specific, right? But the CML reduction technique you talked about, today I'm at the is something that's available in the main guide, because that would be very useful for not just combustion simulations.
Yeah, so for the online people, now I remember. The question is if the CFL adaptation change is already available on the main code, and I need to ask NISO if it is available on the main code already.
You will communicate a full request next week.
Okay, perfect. It will be next week then.
Other questions? We still have a minute. Toby?
Question for the Vance correction. Is the curve following some physical informed style, or is it just like fitted? So I'm wondering if it's just fitted, or you can just automatically like this squares something.
Yes, so the question was about the Vance correction and how this curve actually exists. So basically it depends on 3 parameters that depend on the equivalence ratio, so at the inlet condition. And so you always have, so we don't really know, but we think that these coefficients just come from experiments. And you always have this border of 1000 Kelvin at 1000 Kelvin. And then with the different parameters, you basically just change how high up this peak is going to be, so how curved or flattened it is. The problem that we have been having with the correction is that in the paper, it is not really stated how this curve was developed. So yeah, so we got the coefficients. Depending on the inlet conditions. So that's why we think that they are just determined experimentally or just by try and error.
Okay, I think we better move on. So let's thank our speaker again. Thanks.